Important stuff, lots to do today. Here we go. So you have your exam tonight. Morgan is holding a review in ECA 219 from 3 to 4. Last minute questions about your studying for tonight's exam. If you have not replied to my email that you cannot make it tonight, please do that immediately. I'm going to, maybe around 4 or 5 today, I'll send out the email back to everyone who has a conflict about the reschedule time. Please respond if you haven't yet, if you can't make the test tonight. Otherwise, the rest of you are coming. Can I have your attention? Everyone's attention, please. The rest of you are going to show up between 6:15 and 7:30, same place as all the other exams, and we'll have exam 3. Okay, then tomorrow, mandatory recitation for Friday recitation people is canceled, but that time is now for everyone optional to come to help study for the exam. And this is, Cerny's doing this, right? So this is tomorrow from 1:30 to 3:30. All are welcome, but it's not required like recitation normally is. So this is to help get ready for exam. Then again, Monday, we'll have another review session, 12 to 2. I'll make the announcement. I'll put it on here right now. That will be in ECA 225. So that's also news to you guys too. So hopefully at least one of you guys can make it. 12 to 2 on Monday. Yeah, all of us, hopefully. 12 to 2 Monday. Does that work for at least one of you? So 12 to 2 p.m. and hopefully Allison can make it. 12 to 2 p.m. Monday, ECA 225, final exam. Yeah? I'm sorry? I'm going to send the email out at like 5 o'clock today. Yeah, so you can still respond to that. If you haven't responded to my email, I'll send it out at 4 o'clock today. This is a study session. So now you've really, by Monday at 2, you've really worked hard over the weekend. You've been studying, and now you have lots of questions. That's the best way to come to this. And then continue to do practice problems. There is another, we'll have a homework assignment, say due like Monday at 5:30, so it'll also be open. What's wrong? Oh, you're tired. Okay, so there will be another assignment, the last web work assignment. It'll be due on Monday after the review session, and then so it'll be open with the answers, so you still have time to check it before the final Tuesday night, which is, final exam is Tuesday night at 7 p.m. Neeb. Did I announce that on Tuesday? Submit. Right, I did submit. Okay, I talked about that. Come on. Final exam. Tuesday, 7 p.m., Neeb 105. I guess that's close to core. That's by core. Questions on the schedule of things. Schedule of things. Here to go. Okay, so this last week is kind of the pinnacle of the course because we're bringing together all the ideas and we're talking about the fundamental theorem. So let's, and you did some of that with the homework. This one. Okay, so here's a really helpful way to think about it. So I'm framing this in a really helpful way. So the fundamental theorem is about the total change of an amount. The total change of some amount, okay? And that amount, we'll say, is modeled by the function f of x. Okay? So the fundamental theorem is about the total change of an amount modeled by f of x as x changes from a to b. And what the fundamental theorem says is that amount, that total change in the amount, can be represented in 2 different ways. So we're talking about the total change of an amount. That amount modeled by f of x as x changes from a to b can be represented in 2 different ways. So without looking at your notes or anything else, can you write down the 2 different ways that we are representing the total change of an amount, and that amount is modeled by f as x changes from A to B. Can you do it? Hopefully you can. I've got my yellow sheet today. So the first way is kind of a very straightforward and easy calculation. What is that about? That straightforward and easy calculation. Can you tell me about that? Where is Joseph Holland?
Yes. It is function B minus function A.
I'm so glad I had one more time to call on Joseph. Okay. All right, but what's the idea of that? The final value of the amount minus the initial value of the amount. Remember way back at the beginning of the class, we spent a whole class on this. We spent a whole class on how do you find the change? Remember that? It was all about the computer, like on your smartphone, the memory on your smartphone. How do you find the change in an amount, say a memory on your smartphone? It's going to be the final value minus the initial value. And the final value is?
Would be the final value of function B minus function A.
The final value would be f of b, and the initial value would be f of a. Okay, so now what's the more complicated way? So not necessarily the formula, but just what's the idea behind the more complicated way of expressing this total change? So I'm not looking for like the heavy-duty mathematics, but just the idea behind it. What's the idea or the process behind finding this amount of change in a different way? What's that? Sum of little changes, she said. Okay? The accumulation of many changes, each one computed by m dx. A little change can be computed by the constant rate times the change. And if we sum up all those little changes, we'll get the total change. So this is what the fundamental theorem is about. It's about two ways of computing or representing the total change. As final minus initial, and as the sum or accumulation of little changes. Each one m dx. Hugely important that you have this in your mind. So now the mathematics. So the mathematical representation. How do we represent final value of f minus initial value of f? That's what Joseph said. F of b minus f of a. Okay? And how do we represent this other thing? Accumulation of many changes of f, each one computed by m dx. Let's see. Where is Liam Moriarty? Liam here. How about Jackson? Jackson Merton. Philip B. So what's the math behind this right-hand side? What's the mathematical expression that gives the accumulation of many changes, each one computed by m dx? Yeah, what expression of mathematical expression does that? Integral, okay. Yeah, you got it. Okay, so but x is changing not from 0 to x, but from x is changing from a to b. So this shows what accumulation is the integral sign sum up a bunch of little changes, each one m dx. So we need the rate function for f this time. Okay? So where do we see m dx? Do we see m dx in this? Yes, m dx is right here. m rate times a little change in x. And we're going to sum all those little changes up. S, German S for sum, starting at x equals a, finishing at x equals b. So both of these compute a number, a value, a total change in the amount modeled by f, starting at a, ending at b. Okay, and since they both are computing the exact same thing, they're equal, right? They're equal. Okay, now we can think about kind of the function version of this. The function version of this is now this thing as an accumulation function. Let b vary, right? So let where we're going to stop, let that vary. So we call that x. So then b becomes x, and so now each one of these is an accumulation function, right? So we think of that total amount of change as defined by a changing right-hand side of an interval, right? So accumulation function. And we talked about last time how by starting at a, we force the accumulation to be 0 at x equals a. And we called that the reset, right? We called that a reset. So this is another way to express that same accumulation function. F of x minus f of a. That's the exact same accumulation function as this one. Okay? Now, although the accumulation is 0 at a, the f function, just f, is the amount. So the amount is not necessarily 0 at x equals a. Right? So we have the amount, and if we do a reset at a, then we're creating an accumulation function, right, that is 0 at a. But the amount, now if we're talking about the function, f, that's an amount function, that not necessarily 0 at f of a. That's f of a, right? F of a is what the amount is at a. Okay, so I hope this helps. So that's a really key idea here at Fundamental Theorem. Two ways of expressing the same thing, a total change in a quantity, okay? Or an accumulation function. Okay, so how do we use it? We use it when we get something like this. So the first thing I want you to do is tell the person next to you, what does this whole, as a whole, what does it mean? So explain all the details. What does that expression mean as a whole? And then, based on its meaning, then how can we solve it or simplify it or get it in another form? Okay, go. Tell the person next to you. What does it mean? Okay, that first integral I put up there. So who can explain what does that mean? How about Jeanette? Where's Jeanette Smith? Can you explain to me what that first integral means, Jeanette? Okay. Okay. Did you hear that? That was awesome. Did you hear that? She said it's the total accumulation as x goes, as x goes from -1 to 2, when the rate is this. When the rate is this. So is that a function? Is that a number? What is that thing? Just in one word, what is it? Is it a function? Is it an equation? Is it a number? Okay, I got a function. It's a function. It's not a function. It's not an equation. This is a number. There is a number that equals this. Why? Because it's a total amount of change, starting at -1 and ending at 2, when the rate of change is that function. So that's a number. That's a value. So how do we get that value? Well, now here's where we use the fundamental theorem. So this is what's called an open form expression. It reflects this process of summing up all the little amounts of change. So if we're going to think of it that way, we need technology to get that number for us. Okay? But if we can write this a different way, we could do it without technology. So how are we going to be able to find that number, that amount of change from x equals -1 to 2? If we could figure out what this function f was. If we knew what the function f was, we could just do final minus initial, right, to get the total change. So you practice this with your homework. What is f? If this is the rate, if this is r of f, then what is f? E to the -x cubed. Anything else? If you're not sure, what can you do? That's why we did the mastery test, right? So that we're masters at this, so we can take the derivative and know what the rate of change is. Do you exactly get that rate of change when you take the derivative of f? Yes, you get exactly that rate of change. Therefore, this is a possible amount function. This is a possible amount function that we could use. And so what does the number equal? So we've got the amount. So we want the total change in the amount starting at -1 and ending at 2. How will I set that up? Where is Christina Schaefer? Christina, tell me. I want to set up to actually solve for this total amount of change now. Yeah? Total change in f from -1 to 2 is going to be the final value of f minus the initial value of f. That gives us the total change. So that is a number. It's in exact form. What is that? E to the -8 minus e to the -1. That's a number, and that's the amount of change that you get when... Did I miss something? I see. Like this? So is this positive now? Very good. So just e. E to the -8 over e. Or minus e. Minus e. So this is the usefulness of it. When we have an open form integral expression that's reflecting this process of summing up a bunch of little changes, well, that's nice, and we know what that means, but how do we get that number now? How do we get that number? We used to need technology to do it. Now with the fundamental theorem, we just say, oh, if we have the amount function, it's just going to be the final amount minus the initial amount. That will give me the total change. Okay, what about this one? So if I want to do that, I need some function whose rate of change is e to the square root of x. Okay? But a closed form function with this rate, e to the radical x, does not exist. There is no function that we can apply the mastery rules, take the derivative, and get e to the square root of x. The first one there was, e to the negative x cubed, had that as its rate function. But there is no closed form, basic function that if you took the derivative of it, you get e to the square root of x. It doesn't exist, okay? And in fact, of all the functions in the whole universe, this is the much more common experience. If you were just to take all possible functions, then this as rate functions, this would be much more common than that. So when we're able to use the fundamental theorem to calculate the total change, the problem has to be rigged. It has to be rigged so that this was the answer to a derivative problem that we did, you see? It's got to be rigged if you're going to get a closed form expression to calculate it, okay? Does it mean that this value doesn't exist? It absolutely exists because here is that same thing as a function. Okay, here's that same thing as a function. 1 to e to the square root of t dt. Okay, that accumulation function absolutely exists. That's the blue one. There it is. So if we were to plug in 5, so just because there's no closed form amount function that has that as its rate doesn't mean that this accumulation function doesn't exist. It absolutely exists, and there it is. And so the accumulation from 1 to 5 would be, I need to zoom out on that. There we go. Okay, so we're just going to accumulate at this rate from 1 to 5, and we're going to get some certain amount. So what will it be? It will be, I just need technology to do it because I don't have a closed form for the amount function. So I'm just going to plug in 5 for x. 23.1305. So to use the fundamental theorem to find the total amount of change for an integral, the problem has to be rigged. That rate function that you're given has to be the result of some derivative, like the mastery derivatives. It has to be such that there's some function whose derivative is the one we're given. Okay? If not, I'm still finding a value of total change, but I just can't use the fundamental theorem to do it. I need technology. I have to have technology to calculate that open form expression. Doesn't make sense. Okay, so hopefully that's helpful. Let's look at more complex expressions. So d dx just means the derivative of, right? So the derivative of the integral from 4 to 7, sine 3 cosine x dx. So in order to make sense of this, we have to make sense of the individual parts. So let me highlight some things here for your discussion. What is that? What is in the blue box? Okay, and then what's the whole thing? So 3 questions. I've highlighted a part in red. What is the meaning of that? Then I've put a box in blue. What's the meaning of the thing in the blue box? And then, what would the meaning of the whole thing be? And so what would this equal? What would it equal? Talk about it. Go. Yeah. Yeah. None of this stuff this week is on tonight's test. Oh yeah, the final. So, well, what do you mean? Like, understand? You can't do it. That's the point. You can't use the fundamental theorem to do it. But it doesn't mean that rate function is real, and so that amount of accumulation is real. That's what I was showing you. Yeah, but there's lots of knowledge questions, right, that we ask. Not just computational questions, right? So all semester we've been understanding things. So yeah, so that idea is fair game for the final. Yes. Yes. Hey, where's Carl? Where's Carl? Carl, how about the red part? What's the red part mean? What's the meaning of the red part? Rate of change function. Agree with that? Yep, that's it. Okay, in the blue box, who can explain what that is? Where's Jacob? Jacob Espacher. Tell me about what's in the blue box. Okay. Which accumulation between 4 and 7? Okay, so at that rate, okay, so it's an accumulation of some amount from 4 to 7 where that amount changes at the rate that's underlined in red, okay? So tell me about that. What kind of thing then is that? Is it an equation, a function, a number? What is it? A number. That's a number. It's an amount of accumulation or a total amount of change. It's a total amount of change. Okay, so now what about the black circle and what it equals? I heard someone say it. People are saying 0. Why in the world is it 0? Did you say 0? Yeah, why? Why is it 0? Yeah, that thing in the blue box is a constant. It's a value. So that thing is 0 because that from 4 to 7, that gets a total amount of change, which is just a constant value. Take the derivative of a constant, you get 0. Okay, so good. Next, how about this? Same procedure. So now this integral, is it a constant? No, this is now a function, an accumulation function, right? That's an accumulation function. So our rate, is this one of the rigged ones or not rigged? Meaning, is there a function whose rate of change is sine of 3 cosine t? Is there a function whose... So that's a composite function, right? And when we take the derivative of composite functions, what happens? We get a chained on part, right? We get times the derivative of the interior, which we don't have here, right? We don't have it. Okay, so closed form antiderivative does not exist. But that doesn't mean we're done, okay? That doesn't mean we're done. Okay? But we're going to call it, so a closed form antiderivative doesn't exist, but an antiderivative exists. An antiderivative exists, and we'll call it F. So just because I showed you in the last example, just because an antiderivative doesn't exist in closed form, there's still an antiderivative. There's still an antiderivative. We just don't have a formula for it. Does that make sense? I just showed you that on the previous graph, okay? So we don't have a formula for it. So we'll just call it f of t without having a rule. So we'll call it f of t without having a rule. So then what does that thing in the blue box equal? What does that thing in the blue box equal? No, not f prime of t. So f of t is our antiderivative. So if we take the integral from 4 to x of this function whose antiderivative is f, what does that equal? No, forget about this. We're just doing what's inside the blue box. I'm telling you that the antiderivative of sine of 3 cosine t is capital F of t. So what does that thing equal inside of the blue box? F of x minus f of 4. Fundamental theorem. Okay, but we're also taking the derivative of that, right? We're taking the derivative of that, whatever that thing is. Are we okay? Does it make sense? So now, what is capital F? It's the function, what? Whose rate is sine of 3 cosine t. It's the function whose rate is 3 sine cosine of t. So what's the derivative of that? Sine of 3 cosine t. And what is f of 4? What is f of 4 in general? It's a number. So what's the derivative of that? 0. Therefore, this whole expression equals, sorry, this is x. This is x, sorry. Sine of 3 cosine x. So we don't have a particular formula that we can get for the antiderivative. So, but we know it exists. So we call it capital F. So by the fundamental theorem, that thing in the blue box is capital F of x minus f of 4. The antiderivative evaluated at x minus the antiderivative evaluated at 4. And now this is saying take the derivative of that. Well, we define capital F as the function whose rate is sine of 3 cosine t. So if you take the derivative, you're going to get the rate. You're going to get its rate. And then the derivative of a constant is 0. So the general idea here is it's the derivative of an accumulation function that's accumulating at this rate. What's that going to be? It's going to be that rate, right? So the derivative of an accumulation function is its rate of change. What is the rate of change of the function in that blue box? Sine of 3 cosine t. Okay, so that's what we said. Okay, so I know what you're all thinking, so we'll do another example to next page. How do you get to the next page? Try this one. You can't just write down the answer. You've got to think through the process that I told you to get this one, okay? So, whereas from the last example, you think you might be able to just write down the answer, you can't. So you've got to think through that same process I just took you through to get this one. See if you can talk it out with people next to you. You got to understand what we did. Sorry. That's how you're going to start. That's how you're going to start. Okay, where's Haley Schulman? Haley, can you get me started? So if capital F is an antiderivative of square root of 1 plus x squared, then this expression is the same as the derivative of what? What should I put in here? Almost. Final minus initial, right? Fundamental theorem says that if you have an antiderivative, you can just get the total change by doing final minus initial, right? Final value of the quantity or amount minus the initial value of the amount, which we know is we get with our antiderivative, okay? And so then, from here, we can do the rate of change of each of those separately, because it's just a difference, right? Okay, so tell me something about that. Where is Ricardo? Just tell me something about how can I make some progress on this expression now. So I've got the derivative of capital F of e to the 4x minus the derivative of f of negative 5. So, okay, so this whole thing is 0. So that's just a number. Derivative of a constant is 0. Okay, so now we've got the derivative of f of e to the 4x. What is f of e to the 4x? Let's write that out first. So we'll do some side work here. What is f of e to the 4x? Oh, we don't know because we don't know what capital F is. Can't do that. Sorry. But we can make progress on this. We're doing the derivative of capital F. What is the derivative of the capital F function? One plus x squared, right? But what is our x now? Okay. Is that it? Someone said no. Why no? Because of chain rule. He's on a roll. The guy's on a roll today. Chain rule, right? We're doing f. This is a composite function now. It's not f of x, it's f of a function. This is a composite function. Whenever you have a composite function and you do the derivative, you need the chain rule, right? So we're going to do We know the derivative of capital F is this, but now it's going to be what? Times the derivative of the interior function. So times what? E to the 4x times 4. So that's what that initial expression equals. What? It's the rate of change of this accumulation function. The rate of change, d dx, of this accumulation function is this. So this is the rate of change of the accumulation function in the blue box. Because that negative 5 to that integral is an accumulation function, right? We're taking the derivative of an accumulation function, that's going to give us a rate. This is that rate of change of that accumulation function. So these are more abstract problems, but they're excellent at, we have to practice the meanings of everything. The meanings of all the expressions and what's going, you got to know what's going on. Okay, so these are maybe not the most fun, but very important for your understanding of the fundamental theorem and all these integral and derivative expressions, right? Putting it all together. Any questions on this example? Please ask. Don't ask after class, ask now. Okay, last chance. So let's look at then, let's go back to rigged ones, but harder rigged ones. So ones where, and you had some of these in your little exercise, but we want to come up with a more structured way of doing these. So we're talking about simplifying integrals where we can find a closed form antiderivative, but it's just for harder functions, okay? So recall the chain rule. Says, if you have g of f of x, what's the derivative? Derivative is derivative of the exterior with respect to the interior times the derivative of the interior. So we're going to look at antiderivatives that are like this. If we're looking at antiderivatives that are like this, then we're thinking this way. We're starting with something like g prime f of x times f prime of x, and we're trying to recover that original composite function. So that's the idea of these. So the question is, we're given something like what's over there on the left. What are you going to focus on to recover g of f of x? Which are you going to focus on? Exhibit A or exhibit B if your goal is to get this? If your goal is to get g of f of x, then which one is going to help you get that? This first one, A, or the second one, B? Well, one of them looks almost exactly this, just one slight difference. Which one is it? A, right? A looks almost exactly like your answer. What's the only difference? So we're basically, whereas when we took the derivative, we had two terms, two factors pop out. So when we go backwards, the two factors are going to kind of resolve back into one. So we're going to focus on the one that looks like our answer. And all we're basically going to do is just do the antiderivative of the exterior function and leave the interior as it is, and we'll be almost there. Do you see that? So we're just going to find the part that's like this, and do the antiderivative of the exterior. And we'll basically have it. That'll be most of the work. So what will the approach be? We're going to write the antiderivative of the exterior function, keeping the interior function as it is. And then, like I said, that's most of it. So we have a little mess to clean up, just like constant factors that we have to kind of clean up, make sure they're right. Does the premise make sense? Okay. So this is the same thing I had at the bottom of the last screen. Just keep it in mind. So here's an example. Integral of x cubed, 8 minus x to the 4th to the 5th. And so just a side note here. This is the first time we've seen an integral that didn't have values top and bottom. So they're missing, right? So what does that mean? That means all antiderivatives that have that rate function. The set of all antiderivatives, right? We said for given a rate function, there's many antiderivatives, many amount functions. So when you don't see anything there, we're talking about all of them. All of the amount functions, or all of the antiderivatives that have that as the rate of change. Okay? So here we go. We're going to think of this like g prime of f times f prime, the result of chain rule. And we need to recover the original g of f of x. So what are we going to focus on? So we've got two things here. We've got x cubed. And we've got the second thing, 8 minus x to the 4th to the 5th. Which one of those, exhibit A or exhibit B, is what we're going to focus on? Exhibit A or exhibit B? What's the difference? We're looking for a composite function such that the other factor is like the derivative of the inside. So we want a composite function such that the other factor is the derivative of the inside. So a composite function such that the other thing is essentially the derivative of what's inside. So we're going to focus on A or B? B. And what did we say? We said to recover the original function, we're just going to do the antiderivative of the exterior, right? So we've got g prime, and we've got g prime, and we want g. So just the antiderivative of the exterior. Leave the interior as it is. Okay, so that gives us a first attempt. So we're going to do the antiderivative of the exterior, leaving the interior as it is. What would that be? So how would I get, I'm going to do the so what is the exterior function here? Something to the 5th. So the antiderivative is that same thing to the 6th with, so from your homework, did you come up with that there also would be a 1/6? This is only a first attempt, okay? But this, we're like 80% there. So what are we going to do to see if it's right? Check it. How do we check it? We're going to take the derivative of it. And if the derivative is exactly what we started with, then we've got it. If it's not exactly what we started with, it gives us information to adjust and make a second attempt. All right, so what's the derivative? 6 times 1/6 to the, or 8 minus 8x to the 4th to the 6th times what? Close. Negative 4x cubed, right? Doing the derivative now. Now we look at that check and we compare it to the original rate function and we say, is it the same, first of all? No. What is it off by? What do I have here that I don't have here? -4. This is the problem. So we ask, how do I adjust the first attempt so that the -4 won't be there? What do I need to do now to a second attempt so that when I take the derivative, no -4? We're going to include a -1/4 with it. So if we have a -1/4 and our first attempt, now when we take the derivative, we should get exactly what we started with. And I'm not going to write all that out, but we do. We get all the same thing, and then times negative 1/4. And those, the negative 4, the negative 1/4 become 1, and we get exactly this. So check. Okay, so if I simplify, if I just do one more step, simplify. So then all antiderivatives or all amount functions that have that rate is any vertical shift, right? Any vertical shift included with that function, right? So with that amount or accumulation function, I could move it up and down any way I want and preserve that rate. So to get all of the amount or accumulation functions, we just need to add a constant, and that gives us all possible amount or accumulation functions. Okay, so I'm giving structure to this, but really the idea is we look at this and we say, hey, look, this is the result of chain rule. And what would I have done when I did the chain rule? Well, I would have used the power rule on this and then multiplied by the derivative of the inside. Well, there it is. There's the kind of the derivative of the inside. So if I'm going to undo this, then I'm going to have this thing to the 6th. 1/6 of this to the 6th. But then I need to clean up the mess. You're really thinking hard about how we're undoing the chain rule. We're working backwards from the chain rule. Okay, anybody have a question before we do the next example? Do you follow? Yeah, please. Yeah. Thank you. This should be 5 right here. That should have been 5. 6 times that thing to the 5th, not 6th. Other questions? Yep. Okay, if you're not sure, what can you do? So we've got an answer. We're not sure about it. What can we do? Check by take the derivative. If you're not sure, take the derivative. You should get exactly what you started with. If you do, you've got the antiderivative. If you don't, then you need to adjust and use the information in your check to adjust. Try another one. Last chance, questions? Oh, that's in another file. All right, so I'll make one up. Ooh. Okay, so now this is a ratio, and we know what is chain rule is ends up with a product. So let's start by rewriting it as a product. How can I rewrite this as a product? Sine of square root of x times 1 over square root of x. Or x to the minus 1/2, whatever you want. Okay? But see how if you can make progress. So you're going to do a attempt. Check it. If you didn't get it on the first, then you can do a second attempt and check that. Okay, where's Jessica Sobel? Jessica. Can you get me started on this? So let's first answer. Which is like g prime f of x? A or B? A. And so what are we going to do? We're going to do the antiderivative of the exterior and leave the interior as it is. So what would that be? Yeah, awesome. But too fast, too quick. So let's just do the antiderivative of the exterior, leaving the interior as it is. What would that be? Yeah. Negative cosine of radical x. Do you see that? Antiderivative of exterior is negative cosine. Leave the interior as it is. There's our first attempt. Remember, this is it, right? Undoing the chain rule just really means recovering the composite function. This is almost exactly like it. It's just we got to do the antiderivative of the exterior, which is negative cosine. Now we take the derivative. What is the derivative of negative cosine radical x? Sine of radical x times 1 over 2 radical x. Is it the same as what we started with? How do we adjust the first attempt so we don't have the 2 in the denominator? Am I going to multiply by 2 or multiply by 1/2? 2. Second attempt, negative 2 cosine square root of x. If we did that, we would get the right thing, because now we'd have that whole same thing times 2, and the 2's would go away, and we'd have what we started with. So plus c to be all antiderivatives that have that as its rate of change. Okay, the goal is you're thinking about the chain rule backwards. You're not memorizing these steps and losing the big picture by getting so focused on these individual steps. What do I do next? This is just to help you, to guide you through it, but the real idea is, this is a chain rule derivative. What was the original function? That's the mindset we want. This is a chain rule derivative. What was the original function? What function's derivative is that? So try to keep that in mind as you're working through it. Okay, so example. Wrong one. No, I'll find it. Not exact rate of change. Topics. This one. Okay. A culture bacteria in a particular dish has an initial population of 250 cells and grows at this rate. Okay, I want to find the population function at any time t greater than 0 days. So what tool or tools do I have? I've got the rate of change. I want to build a population function. How do I begin doing that? How do I begin doing that? If you have a rate function and you want to know an amount function, what tool do we have for that? Josh Gonzalez. Joshua Gonzalez. No? Jacob Loeffler. Jacob Loeffler. Patrice Miles. Luis, I've got this rate function. Can I set up something that would be a population function from this rate function? Accumulation function, right. So how do I do that? But okay, so what's going to be, all right, let's skip off the rate. Let's not do those for now. So integral of? Okay. Oh, we need the same as that, dt. All right, since our independent variable of the function's t, we want to use something else here. X is fine. Okay, so now what are my limits? So is it going to have to do with the 250 or is it going to have to do with time? Time. So time we want to start at 0 until t. Now, what I have here, what is the population of bacteria at time equals 0? What is the population of bacteria at time equals 0 for what I have written here? For what I have written here. We get a reset. Remember, if whatever this is, we get a reset at 0, meaning that at that value, the accumulation will be 0. But we want what? What population do we want at time equals 0? So what can we do? Just add it. So it's going to be the 250 we start with plus how much accumulates, which starts from 0, right? So the 250 we start with plus how much accumulates at that rate, which starts at time equals 0 and has an accumulation at that time of 0. So this forces our initial amount to be the 250 that we want. So the initial amount plus the accumulated amount in t days. Okay, but we want a closed form of this function. So this is open form because it's integral. So can you get a closed form of this function? That would mean what? A function whose rate of change is this. Can you do it? Can you get a function whose rate of change is 50e to the point 3x? Work on it. So it's like a mini undoing the chain rule. It's like a mini undoing the chain rule. You gotta think, what function has that as its derivative? So what we're really asking is, in general, what's the antiderivative of e to the 0.3x? What function in general gives us a derivative of e to the 0.3x? E to the 0.3x, right? The e function is just its own derivative. So a first attempt would be 50 times e to the 0.3x. Now we take the derivative of it. Derivative is 50 e to the 0.3x. But then times what? 0.3. So how do we have to revise our initial attempt so that the 0.3 is not there? So we're going to take that first attempt and we're going to divide it by 0.3. And then when we take the derivative, we'll get that. So it's going to be 50 divided by 0.3 times e to the 0.3x. Now here's some new notation. Okay, careful, watch. So what does this say to do? It says take that antiderivative and do final minus initial, right? Total change. So we want to plug t into this, and we want to plug 0 into this and subtract, and that's what this thing equals, right? So this means that, right here. You put a vertical bar over here, and you go 0 to t. And what does that mean? That means plug t in and get the final value of the quantity. Plug 0 in, get the initial value, and then subtract. That's what that means. So I'll write it in the next step. So it's going to be 50 over 0.3 e to the 0.3 t minus 50 over 0.3 times e to the 0, but then plus my 250. Did you catch it? So this is just applying the fundamental theorem. The antiderivative evaluated at t minus the antiderivative evaluated at 0. Final value minus initial value. Final minus initial is one way to compute a total change. Also shown in open form as the sum of many little bits of change. All right, so that's our accumulation function of cells plus the initial amount of 250. So we can simplify that. What is 50 over 0.3? Let's go with 500 thirds to be exact. Minus e to the 0 is 1. So that's 500 thirds plus 250, whatever that is. So that's 750 thirds. 250 thirds, check my math. That's 750 thirds minus 500 thirds is 250 thirds. I think that's right, but I could be wrong. So that's the population function. We built it by the initial amount plus the accumulation. And then we got the closed form version of the accumulation using the fundamental theorem. And now population after 10 days is easy. So how do we get the population after 10 days? We just use the function, right? That's b of 10. That's just asking for b of 10. Okay, so listen up. There's one more topic that we need. So there's going to be a 15-minute video. There's going to be a 15-minute video, okay? And then there'll be the web work homework that'll be due Monday night. So you can work on that while you're studying. So this week's stuff is a big chunk of the final exam. I'm going to post a review outline for the final and some other studying tips on Blackboard, so just read carefully. Thanks for a great semester. We'll see you tonight. Then how do you have to find the value? You're going to put 10 in the integral? How are you going to get the number? How are you going to get the number? More efficient population plan. That's inefficient. Every time you want to do one, you have to use a calculator. So it's like the calculator has to do that process of adding all the But this is just like rapid fire. Like plug in a number and it spits out population of different numbers. Rather than every time thinking about some of it. Yes, sir.
How did you get this number?
250, there's that plus that. Those are both constants. This is negative 50 thirds, which I think is, yeah, negative 50 over 0.3 is
Negative 500 over
500 thirds. And then this is 750 thirds, right?
Yeah.
So 750 minus 500 is plus 250. Should be plus 250.
Wait, so that's wrong?
Yeah, it's wrong. Did you think it was plus 250?
I thought there was something wrong with it, but I wasn't sure what it was.
It should be plus 250 because this is positive and this is negative. This is positive 750 thirds minus 250 thirds.
Yeah.
No. 500 minus 500.
Yeah, I didn't think it was 250. I thought there was something wrong.
So it's plus 250, not minus 250 thirds.
Okay.
Do you see?
Yeah.
Yes, sir.
This final, kind of overlaps with my finance.
Okay.
So my finance, 231 finance is from 6 to 750.
Okay.
And I was wondering if possible, can I come in at 8?
Yeah. Yeah, that's okay as long as you. I mean, we usually stay longer than the allotted time, so you should be okay.
Okay. So
Yeah,
it should
if
be-
worst comes to, yeah, it should be fine.
Okay.
And if we absolutely get kicked out of the room and you're still working, we'll figure something out.
Okay.
Yeah, you'll be fine.
Thank you.
Yes.
I just wanted to see when the grades will be upgraded for the mastery exam that I took earlier today.
Do you pass it?
Yeah,
I can do it right now if you want.
I just wanted to make sure.
So I forgot what attempt it was for you.
That was 4. It was a 4.
Okay. So, and did you get some wrong?
I think I was 9 out of 10. 9 out of points.
So you get like basically you got a 72% on it
Okay.
because you'll get. And this is the fourth attempt, right?
Yeah.
So you get 80% of your score. So if you got a 90, yeah, you get like 75. You'll have 75.
Alright, sounds
But when I go through all this paperwork on my desk, I'll get that grade in.
good. Okay, sounds good. Thank you very much.
You're welcome.
Appreciate it.
Sure. Hi.
I usually take my exams with the DOC on Fridays, and unfortunately this week I have to take my OChem exam tomorrow as
Okay.
well.
Okay.
I have class at 9 o'clock and 12, and I was already planning on missing my 12 o'clock one, but I have to work at 3, and I have to take I'm gonna have to take OChem and this exam one
Okay.
after another.
Okay. So your availability tomorrow is from when to when?
I have class at 9 to 10, and then I have to take an OChem exam, and then I work at 3.
Okay.
And I didn't know.
So for both exams, what is your window of opportunity to take both exams? From when to when?
From 10 to probably 2:30.
Okay. Yeah, we should be fine. So you're gonna take the other one first, right at 10?
Yeah, I guess so.
Or you could I will be around. You could come and take mine first around 10 or 10:15.
Okay.
Would you rather do that?
I need to like figure out which one I'm
So
gonna take
yeah,
first.
so you have the option. You can. I'll be back in my office a little bit after 10. You could take it then,
Okay.
or you could take your other exam first and take it around noon. Or
Okay.
noon.
Do you think that's gonna be like a good amount of time? The last exam I had this kind of same issue happen, and I had to leave to go to work. And
I think 2 hours is going to be enough.
Okay.
So you need to be walking out of the room at 2:30, or you have to be somewhere at 2:30.
I have to be somewhere at 2:30.
To be somewhere at 2:30.
Yeah, like I would have to leave here to be there
At
for 3, but leave here at 2:30.
okay, so you have to be going to your car at 2:30.
Yes.
Okay. Yeah, as long as you're starting the math exam by 12:15 or even 12:30, that gives you 2 hours. It should be enough time.
Okay. I think my chem exam I have up until 3 hours, so I don't plan on taking that long, but if I do go over, is there really not? I understand if there's nothing I can do about it, but I wanted to ask.
Well, I mean, tomorrow's really the only day to take it, and you can't take some of it and then wait a long time and take the
Yeah.
rest. So we're just gonna have to do your best with
Okay.
that time that you have.
Okay.
But I think 2 hours or 2 hours 15 minutes should be enough for the exam.
Okay. Thank you.
So just let me know when you're gonna be coming, okay?
Okay, well, thank you very much.
Yep. Okay, you bet. Great having you.
Likewise. Something that would have helped me, I wrote up this long review, but I texted the person that distributed me.
Okay.
Is if the homework had been posted like the day, like immediately after class.